Okay, well, I guess you'll. So I've got some practice data just downloaded, unprocessed, and what we'll do is just process it. This is Andromeda Galaxy M31, and yeah. So one of the issues I have with working with practice data is that it's always the stuff that you find online. It's always perfect. And you don't get any of the issues that you would normally encounter if you were to go through this process with your own data. You find that you've got these awful light frames, and some of your darks aren't any good, and some of your flats aren't any good. We haven't got many lights, we don't have many dark frames, we don't have that many bias frames. But yeah, I've looked through this. I think the data's actually quite good. So we'll just give it a quick go through. This was all taken with a Canon camera, and the guy who took it was kind enough to upload his raw files, his darks and his bias frames up onto the internet. As you can see, we've got about 8 light frames which we'll pull in. These are going to be colour frames taken with a Canon camera, so there's no multi-channel, and we only have the one session to work with. We don't have any flats, we have some darks. It's provided, and we just have 5 of those. So you kind of sort of think, is that going to be enough? Well, hopefully it will. And we have some bias frames. I've got more of those, but about 9 of those or so. That's good. So RGB frames. So this has already got the colour in each of them. Have a look. As you can see, there's the red and the blue are quite aligned, but the green is off as far as the intensity is concerned, which is interesting. Have a look at another one. These all look very similar, don't they? What you would normally do if you were really going for taking these pictures and ensuring that you have the right data is you would inspect each one. Look for things like satellite trails, artifacts that might appear in the image. But as you can see, these look all identical. They're 8-minute exposures, which is pretty high. That's pretty good. Have a look at some of the darks. We don't see a lot of noise in there at all. You can see that there is a kind of a light source just there on the right. Have a look at the bias frames, and we just see we have to go in pretty far to see any sort of data. Well, that is data that we're going to be subtracting from these light frames in order to get the clearest signal to noise ratio. So let's build our master bias and master dark frames. We go into Calibrate here and we'll create the masters and assign them to the lights. Let's do that. None of this is going to take very long, so this won't be the longest video or stream that I've done. So let's done the master bias. It's appeared down here, and that's just doing the master darks. That's integrated, it's basically averaged, taking median values from those. Okay, so that's step 2. We go on to analyze stars. I'll just raise that slightly. Got plenty of stars in this particular field of view. So it's just going to take each light frame and perform an analysis of the stars, get an idea of the quality of each of the frames. These are all really good quality frames, so perfectly in focus, at least visually. Okay, so now we're going to register those frames. I'm just going with the defaults on this because we essentially have model data. Be a nice picture at the end, I'm sure. See, registration didn't take very long at all. Now we'll normalize those frames. This will probably be taking out and readjusting that green to coincide and have the correct intensity. Obviously the sensor on the Canon was picking up and it was much more highly sensitive to green than it was to red or blue. Like I say, this is going really, really quickly. So that's done. Now we can take a look at one of these. So up here we have linear, calibrated, registered and normalized. So we've completed all these steps. So we can take a look at, say, this frame and see after it's calibrated, it doesn't appear to be that much change. When it's registered, what it's effectively going to have done is you can see a slight change there between the pixel where the stars are. When I move back to calibrated, you'll see you see the stars move just ever so slightly. And if we were to take, it won't have done that on the reference frame. If we can work out which one was selected as the reference frame. So the reference frame is the one that says, right, this is the central frame, and then it's going to just apply a transformation to all the other 7 frames to essentially ensure that when you come to stack and you pile each of those images on top of each other to get that to get the alignment of the stars in place, that they will stack perfectly together, and we have the same view of the sky in each picture. And in normalized, I'm expecting here this is we'll have adjusted our green, and it has, yes. So in the histogram here, you may have noticed if we just go back. Yeah, the green was over here. It's obviously that we're far more sensitive to green on this imaging sensor on the Canon. I don't have that with my monos because obviously I'm using a filter and using a mono camera. So this is kind of new to me. But the normalization, one of the steps it's done is it's taken that, and it's not to say that it doesn't do that with my mono frame. So when I take an Rgb, I'm sure that this software is looking at the intensity of each of those frames and saying, let's normalize this peak of the image so that it all appears in the same place, so that when you come to stack, that everything looks good. So these are the individual images. Over here on the right, we can change the amount of stretch and the various parts of sort of simple algorithms which allow us to basically change kind of sort of brightness. It's like the gamma in a way, as to how much this is pure white as opposed to, say, a medium grey. And it does help if you're doing some of the later tasks, such as removing light pollution and trying to get a better background, calibrating the star colour. It's sometimes makes your job easier. Anyway, so let's carry on. Let's integrate all these. Some people will just be really happy to just get that image. That's an 8-minute exposure. We're going to combine 8 of them, so we're going to get about an hour's of exposure, and hopefully be able to remove noise from that integration to further increase the amount of detail that we can see. So let's go with the integration. This is M31. Let's call it Andromeda, because it's while it is mostly M31, you've got the other 2 satellite galaxies in there, so I tend to prefer to call it Andromeda. Let's take a look. So yeah, you can see what's going on. It's essentially loading all those frames, and now it's just piling them onto each other. A way of doing this, or a simple way of thinking about it, is if you were to look at all those frames and print them onto transparent sheets, then you're just piling those transparent sheets on top of each other, and because they're not completely opaque and you can see through them, you're seeing a certain amount of extra detail from the combination of all those 8 frames. And obviously it does a bit more mathematics in the background, which a lot of settings that you can fiddle about with. But the software these days, you notice it's got this automatic setting. It kind of makes a lot of decisions on its own. So we've got an integration RGB channel, which I think is just automatically loaded there. Let's just load it again. We can go back down, reduce that stretching, to see what we have. It's rather nice, really. Just the way you can do this on the fly. Because everything I'm doing on the right hand side here is not actually changing any of the files. It's simply providing a change to your view. So let's go into tools. This looks like, I don't think there's anything to be gained from going for a correct vignetting procedure here, but we might go and try and do this, remove light pollution. So let's bring the stretch up as far as possible, and go into remove light pollution. So the task here is to select at least 5 area select boxes, and what you should try and do, unfortunately Andromeda is so huge that it's difficult to really tell where it ends on any frame. I wouldn't be able to grab this frame in a single shot. I'd have to mosaic it on my particular telescope. Andromeda being a galaxy that is practically visible with the naked eye if you have good eyesight and good seeing conditions. When I say visible to the naked eye, you can see it as a smudge in the sky. You might not notice it's there because it is a smudge. So let's go and calculate here on this. So what it's doing is it's looking at the areas inside here and it's trying to build a map of how to change the background to remove what it thinks might be noise, and that's the reason why you don't want to do that, because that's not noise. That's obvious to us, but it's not obvious to it's not obvious to mathematical algorithm. It's come up and said, well, these are a bit yellow, which means they're sort of borderline, and these are red, which is saying these are outside. I calculated a way of modifying this map, which I think we can take a look at. Yeah, so it's basically sort of said, this is how I'm going to modify it. That's the correction model. However, this didn't fit in, that didn't fit in, and this one and that one, that one, that one, that one, not really fitting in so well. So let's go back to the image. Let's work on the red. So we've got one here and we've got one there. So what I tend to do when we get reds, and I know that there isn't nebulosity there, is just replace them with a few more. And what we can just do is just increase the flexibility slightly. So the flexibility, the higher the value, means that you can, there's more sort of flexibility. With the lowest flexibility, you're just going to get a, and with a higher flexibility, then there's, you'd be able to have, say, multiple peaks within the diagram and so on. Let's give that a go. Okay, so we still have some reds there. Try and pull some through. The ones on the edge, where they're yellow, it's probably doing that because it hasn't. It's at the edge of the mathematical model. So that's where the graph is either. So if it's looking at sort of a polynomial, it's kind of not really spaced out. And it's just tending to infinity on in the algorithm. So a way of sort of just getting rid of that is around the edges, just put more smaller boxes. Maybe get rid of the larger ones and replace them with smaller boxes. And essentially everything inside the boxes is data that is being used to then modify the image as a whole. So putting smaller boxes around the ones that are yellow or even red can be a way of sort of smoothing out the algorithm. These smaller ones might then obviously go red or yellow, but you know, if you've got a well-framed image, then you might just crop that edge anyway, or if you've got loads and loads of exposures, as we saw the other day, and your frames are moving around, then you don't want those edges anyway. You're probably going to want to crop them off your final image. Let's do that recalculation there. Let's see. This is an iterative process. You can just carry on going forever. The important thing is to just avoid the nebulosity areas within that. So I'm happy with that. I know we've got some reds. Let's just remove the reds to find the calculation again. We are looking at a stretched image. So this isn't necessarily the intensity that we're going to look at, but you want to work with a heavily stretched image when you're doing something like this, because you want to avoid that nebulosity. So essentially it's just saying bring out all the nebulosity, and then we can look at it. But I mean, we can go back to how it was before, and you can see that. So let's save that. So yeah, it's, we haven't done a Calibrate background, but it seems to say, right, I've done light pollution correction, and it's always puts in CBG here. I don't know whether that's a bug or whether it's the fact that it's actually done a Calibrate background. And one of the things that I've also noticed is when we come to actually then do a Calibrate background, let's bring up the stretching here again. I don't see that all that much change. So I have a feeling that within the within the remove light pollution, that it's actually doing a calibrate background as well. So in any case, I still go through and do calibrate background. First time I did this, and I think I still do it to this day, is when I'm selecting areas, I try to avoid bright stars because I'm calibrating the background. So really, I want areas that are predominantly background. And if I were to put bright stars into these areas, then would I not somewhat break that algorithm? Perhaps not. Perhaps it's got some kind of star detection and says, "Oh, that's a star, so I'm not going to measure the average ADU in that area." And yeah, but that's a star, so I'm going to discard that. Maybe it does, maybe it doesn't. I don't know. So I still, to this day, when I'm selecting boxes, when I'm cleaning windows, I avoid the bright stars. And maybe that's the reason why I don't get much of a result from this particular stage. Like I say, did you notice anything there? I didn't. Let's go with it. Okay. Let's remain. Calibrate star colours, I think, certainly is something that's worthwhile doing. And as I've said before, what I've seen when people have done this, I've seen them just select the entire picture. Andromeda, though, is so bright that I would rather just select stars, because what we are doing here is looking at stars. It's going to say, right, I know galaxies are stars, but there's so much of a huge amount of stars in Andromeda, and really we're sort of still wanting to sort of sort out the background. So what I think the algorithm here is doing is it's going to go and identify stars in all these boxes, and it's going to say, well, I know that in the sky so many stars are red, and so many stars are like our sun, more of a full spectrum, and it's going to say, right, I need to adjust the colours to essentially match that overall ratio of stars, identify which ones it thinks are red and which ones it thinks are normal stars. And you'll see this when we do the calculation. It does this through a number of iterations. Iteration 1, 2. So you notice a slight tone change there. It's kind of sort of yellowed out Andromeda just ever so slightly. I think this is before, and what is essentially said is align them according to this line by making modifications across with these settings, which you can now if you wanted to aesthetically change them. You can do some aligning here. I'm going to leave that. I'm going to leave it as it is. Remember, this is a stretched image as well, so it's actually looking pretty good. So let's save that. We can make this slightly bigger by doing that. So I'm quite happy. As I say, when you work with practice data, so this is what you are essentially seeing when you look through the eyepiece of, or through your binoculars at Andromeda. Yeah, it looks like a big star, or you might be able to make out a smudge. And it's only with imaging technologies that you can start to bring out that kind of detail. I'm sure if you got a really, really big telescope, then maybe you'd see something like that for real. That's just, I'm not even going to do anything GIMP with this. I'm just going to find something that looks reasonably nice here, and then that'll be, yeah, that's got too much sort of saturation. Yeah, I think we'll go back down here to that one. So yeah, let's bring that away. Yeah, it's a nice size. That's M31, the Andromeda galaxy, and its satellite galaxies. Right, well, yeah, cheers for following this along.